Giacomo is the chair of the session. So thank you very much, Giacomo. I leave the podium to you.
Okay, thank you, Guido. We have several high-profile speeches today. So I will start with the first speech is design of scheduler plugins for reliable function allocation in Kubernetes. And the speaker is Rui Kang. Good morning, Rui. And I will share your video presentation, and then we will have a few questions afterwards.
Giacomo, we don't hear the audio.
Yeah, I know. Let's try again.
Hello everyone, my name is Rikan from Kyoto University. Today I would like to introduce our demonstration test by the design of scheduler plugins for reliable function allocation in Kubernetes. This is outline for today's presentation. Firstly, I would like to introduce the background of this demonstration, then the motivations and the goals. And the most important part is the details of the design, and then the demonstration of the paper and then the summary. And this is the application deployment in the current model web services. And the model web services are implemented by the applications deployed in the services. And there are mainly three deployment areas. And at first, in the traditional deployment, the applications are run directly on the physical service, shown as here. And it's difficult to define the resource boundaries for different allocations. Then the second one is the virtualized deployment, and it runs multiple virtual machines on a single physical server. And each VM is a full machine running on all the components, including the OS, libraries, and application. And the applications are run in the VMs. Then the container deployment now. This is similar to a VM but lightweight, and it decomposes from the underlying infrastructure as applications are packaged and run in containers. And for scheduler in Kubernetes, I would like to introduce Kubernetes at first. So Kubernetes is a portable, accessible, open source platform of managing the containerized workloads and services that financials both the declarative configuration and automation. And in the Kubernetes, pod is the basic execution unit of Kubernetes application. So pod includes several containers. And the scheduler is a component in Kubernetes which matches the pods with the nodes so that the pods can be run by Kubernetes. And the scheduler provides the following functions. Firstly, it finds the set of nodes where it is feasible to schedule the pod, called factor, and it ranks the remaining nodes to choose the most suitable pod placement. And the scheduler assigns a score to each pod that survives filtering basing the score on the active scoring rules called score. And finally, the scheduler assigns the port node with the highest ranking, and it keeps the enough resources for the port. The motivation of this paper is to design a scheduler in Kubernetes, and the scheduler must allocate the VMs to suitable locations according to the results obtained by mathematical calculation. And in addition, different users have different requests of services with different quality requirements. The expandability of the scheduler is necessary to support multiple models without restarting the scheduler in case of service interruption. However, no tools in Kubernetes can be used now to deploy the VMs to nodes by using the results from multiple allocation models, and it can only use a simple logic to decide the locations of each pod. And our goal is to design and implement a scheduler to allocate pods according to calculation results from multiple reliable function allocation models based on scheduler framework in Kubernetes. And the scheduler provides an intermediate layer to convert the results from different models to the pairs of pods and nodes so that the Kubernetes can deploy the pods to the nodes. And new allocation models can be added to scheduler without restarting the scheduler to avoid the interruptions of services. And this is the structure of our demonstration. And there are mainly two components in the structure, a scheduler pod and several model pods. And the scheduler pod is the main component in the demonstration, and it receives the query of the pods waiting to be allocated. And it determines the allocation of them computed by the request models according to the current network status. And in the model pods, there can be multiple model pods according to the user requirements. And different model pods use different mathematic ways to calculate the allocation results. And it receives is the network status, for example, the available resources of nodes and links, and computes the allocations. And it converts the network status from the scheduler pod to the recognized data of calculators about the calculator, so it can be contacted in the model pods, or it can be independent with the model pod. And the model pod converts the calculation results from the calculators to recognize the data of the scheduler pod. And for the scheduler pod, there are mainly three components in the scheduler pod: the scheduler container, the data collector, and the database container or shared volume between the above two containers. And the scheduler container implements 4 plugins in Kubernetes scheduling framework, showing here. And the blue part is the implemented plugins in the scheduler containers. Firstly, the sort plugin. Sort plugin records the pods corresponding to VF requests in the waiting queue. And the pre-score plugins in our scheduler marks the non-schedulable nodes and compares the existing data and the current data. The score plugin gives the scores for each node in allocation, and pods corresponding to VF request are allocated to the node which has the highest score. So normally the score plugin limits the final scores of nodes to a range from 0 to 100. About the model pods. The model pods has two main functions: the data conversion, and which converts the data, for example, a list of node names, a list of VF nodes, and other network parameters to the recognized form of the calculators. and then it uploads the location results to the scheduler port. The model port has two tabs: the calculator in the model port and the calculator out of the model port. For the tab that's the calculator included in the model port, it receives its data from the scheduler port, then calculates the results, and finally sends them to the scheduler port. For the tab that's the calculator out of the model port, the model port starts its required calculator ports and manages their life cycles. And the model port and independent calculator ports are created as jobs. The job in Kubernetes creates one or more ports and ensures that a specific number of ports successfully terminate. The model port job are started as cron jobs by the administrators, which run and upload the results on a regular interval. If the prescore plugin requires to update the location results according to new network data, the model ports are created as normal jobs by the plugin. And for the database, in the scheduler port or the shared volume between the components in the scheduler port, and it has three types of tables. Table 1, the table named node. There's only one such a type of table here. The table node contains the node name and unique identification number, and the node resource information, for example, the maximum CPU, memory, and the allocatable, available CPU and memory in the node currently. And the table request. So one request has such a table. So it contains the location results of the VNFs in this request, collected by the scheduler port from the model port, and then the availabilities of nodes in the request, and then the application number and correction timestamp, then the name of the request model for the requirement of the model port. And then the table request model. There's only one table request model here, and it contains the allocation results, update intervals, and the image names of the model ports, and initialize the commanders, and the correspondences between the models and the request, which ensures that one request is computed by one mode. Now I would like to introduce the communication between different components. And there are three types of communications between components. The firstly is the communication with Kubernetes API. The data character and the scheduler containers in scheduler pod and some model pods need to communicate with the API server or the metrics server by the Kubernetes API. And the communications are implemented by REST and Kubernetes libraries. The second type is the communication with the database. The model pod, scheduler application, and network data character in the scheduler pod need to be communicated with the database. The internet protocol address and port of database are given in advance. They use the TCP connections to communicate with the database. The last type is the communication between model pods and calculator pods. The communication between model pods and the calculator pod can be implemented by different types of the protocols. And here in this model, we recommend that we can use the gRPC, since the model pods are implemented by the Golang language, and for the model pods, we can use different programming language. For example, if we want to solve it by some expert methods, such as using Cplex, we recommend that we use POLP package for Python. And if we want to fast way to calculate the result, we can use C++ to implement the heuristic algorithms in the calculator pods and model pods. and the model pod remotely calls functions running in the calculator pod and receives the results from them. And this is some results for the demonstration of this paper. So we prepare the software in this list, the scheduler, and we implement the scheduler the database.
Pronto.
And the demonstration run on a 4-node Kubernetes cluster, includes 1 master node and 3 worker nodes. And the steps are listed here. So we prepare 2 requests with different allocation models. Request 1 has 5 VNFs, and request 2 has 3 VNFs. And we ran the designed scheduler. You can see the database port and the scheduler port are listed here, surrounded by the red box. And this is demonstration. The next step, so then we calculate the ports into request by YAML configuration field, and the model port are created by drops and run. After few more minutes, the allocation results are written into the database. The list of ports are allocated by scheduler is shown finally. So we observe that the final allocation are the same with the results from the models. It's here, we can here, and then the nodes. This is the calculation result, and this is the final allocation result by Kubernetes. And this is the database node, the table node, and this is the model jobs corrected by running predictably. This is the summary of our presentation today, and this paper designed and implemented the pod scheduler in Kubernetes, and we introduced the structure and components in the scheduler in details. Then we provide a demonstration of the introduced scheduler. Okay, thanks for listening. I'm waiting for your questions and comments.
Thank you for your presentation, and we have time for a few questions. Perhaps I can start with one question, and one important point that is generally made about microservices and the serverless deployments is that you need extremely fast startup time, because everything is deployed on demand. So have you evaluated the cost of your scheduler and in general of scheduling, optimal scheduling when it comes to startup times?
Okay, thanks for your question. You're right. So it is important to deploy the microservices in fast time. And so for traditional deployment, as a comparison for traditional deployment, always need 0.00405 seconds to deploy services. And for our demonstration, it needs about 1 or 2 seconds to deploy the services. It depends on the method you use. If you use a heuristic algorithm or some approximate method, it will take you 1 or 2 seconds or less than 1 second if the numbers of the VNFs and the scale of the network is small. And if you want to get solution extract placement, if you use ILP or MMP approach, it will spend you several minutes or several hours. So that depends on your approach implemented in the model pod. Is that clear for you?
Okay, thank you. Do you have any other questions? So no other questions. So thank you for your presentation, and we can move to the next speaker, who is Paolo Comi, presenting increasing network reliability by securing SDN communications with QKD. I will start the presentation in a while, and then we will have time for a few questions.
Hello, my name is Paolo Comi, Research and Innovation Manager at Italtel. Today, I'm going to present to you the paper Increasing Network Reliability by Securing SDN Communication with QKD. In this paper, we present how to make SDN much more reliable with QKD, a brief introduction to QKD, the illustration of the prototype and the testbed environment, and the description of our approach for the integration of QKD and SDN, and finally, the demonstration of this solution in a real network deployment. First of all, I wanted to acknowledge the European Institute of Technology that made it possible to realize the first QKD prototype thanks to a collaborative innovation action. SDN is a strong idea for the design of communication networks. We have a centralized control plane and a distributed data plane. However, SDN exploits an architectural single point of failure. So we have a critical requirement to secure the communication among SDN functional elements. A possible way for securing this communication is by using quantum key distribution for providing symmetric encryption keys. In this way, we can secure the links between the SDN controller and the agents. In other terms, the links represented as dotted lines in this diagram. A brief introduction to quantum key distribution. Quantum key distribution is a technology that uses quantum mechanics for transmitting a sequence of bits between 2 points, Alice and Bob. The transmission of these bits is absolutely confidential, thanks to quantum mechanics characteristics. In this way, QKD can deliver encryption keys that are symmetric, absolutely confidential, and quantum safe. For understanding how QKD works, it could be useful to analyze the differences between bit and qubits, or in other terms, the differences between the classical domain and the quantum domain. In a classical domain, a bit can be represented by a square wave with two values, 0, 1, on or off. In other terms, a single piece of information. A bit is able to create, read, and reproduce. On the other hand, qubit can be represented by a distribution of probability in the space and can be created by a combination of two information, a base and a state of polarization. This makes very, very hard to not only to create but also to read and to interpret in the right way the value of a qubit. The prototype is illustrated with this logical diagram. We have a transmitter and a receiver interconnected by optical fiber. This prototype is able to be integrated in any communication network, not only in lab, and indeed it does not use dark fiber but production fiber in a real communication environment. And thanks to the integration with the SDN, it is also able to be integrated in any topology of optical network. And finally, it is compliant with the standard ETSI specification. The QKD is a very novel technology, and it means also that the dimensions and also the cost are very, very high. Elements composing the technology are a laser, a polarization state generator, a single photon avalanche detector, and an industrial computer for collecting and elaborating all the information and interacting with the classical domain for delivering the encryption keys. The testbed environment was provided by Topix, that is an internet exchange in Italy in Turin area. QKD insertion in an SDN network can be represented in this diagram. We have the SDN controller in yellow and the SDN agent in green. On the physical side, QKD modules are connected with the optical fibers, and the key management is the middleware layer that is able to interact with the physical QKD modules and the applications delivering the encryption keys. As I said, our solution is ETSI standard compliant, and in this slide are represented the main standards we have used in this work. Now it's time to understand how QKD can be used by applications for getting encryption keys. First of all, the keys are extracted in a session-based relationships between the application and the key manager. The first step is to create a stream association between the two endpoints, Alice and Bob, through the middleware and the SDN layer. The central phase is the extraction of the keys generated over the quantum channel, and finally the termination of the session. I'm going to demonstrating this dynamic with the tracing extracted from the testbed. We have Alice, Bob, the initial key stream association, followed by the generation of the keys over the quantum channel. You can see that we have the same key on the both sides, and the increase of the dimension of the key thanks to the interaction with the key manager and the quantum layer, and finally the termination of the session. The system that we used for the demonstration of the integration of QKD and SDN is represented in this slide. We have implemented two different nodes, node A and node B. In node A, we have the SDN agent and the SDN controller, and in another node, node B, another SDN agent. The communication among the SDN functional elements is made secured by using symmetric encryption keys. First of all, we have a pre-shared keys stored in the SDN agents and in the controller. These are used in the first stages of the communication. The SDN agents evaluate if they need new encryption keys, and in this case, they ask the key management and the QKD environment to provide new keys. And finally, these keys are used for the communication among SDN elements. In our demonstration, we decided to use pre-shared keys for the communication inside of the same node, and to use QKD generated keys for the inter-node link. The dynamic is represented in this sequence chart, and it is composed by an initial phase of using pre-shared keys and the negotiation and the understanding that in our case SDN controller and SDN agent B need to renew encryption keys thanks to the presence of a QKD layer. New keys are generated in the same way as I have already presented and finally used for the communication. Another video represents this dynamic. Agent A uses a pre-shared key for communicating with the SDN controller. This is the pre-shared key and the initial node configuration sent to the controller in an encoded way. The controller receives the encoded message that is able to interpret using the pre-shared keys. On the other side, agent B starts the same communication, but in this case, it is requested to generate a new encryption keys, and they are actually generating them, and keys generated are now available to the controller and to the SDN agent for the communication of the over the interlink node in a secure way. In summary, in our work, we started from SDN, that is a great idea for network design, and QKD, that means a secure distribution of symmetric encryption keys. So the integration of a QKD and SDN results in a more reliable network because of secure communication. Moreover, QKD is available for any application requiring unconditional security. And SDN and QKD integration means improved value for the network infrastructure provider, making them available to provide high-value security services to their customers. Thank you for your attention, and feel free to contact me if you need more information. Goodbye.
Giacomo, you're on mute.
Yeah. Yeah, sorry. We have time for a few questions, so please use your chat or just open your mic and put your questions. I can start with one quick question. I've seen in your presentation that there is some standardization effort, which generally means that there is some interest from the market. And in your opinion, what is now the demand of the market with respect to QKD technology?
Okay, thank you for your question. Indeed, I think that QKD is a very new technology, a very old concept about a new technology for secure services, and there is a strong activity in standardization. Nonetheless, the market has in some way to be educated to the need of increase in security. And this is the situation. There is a huge work with this new technology, with a lot of investments, and a market that is starting testing the technology for understanding which services can be implemented for making much more secure the communication and the data.
I would also have a question.
Please.
What is the kind of delay that you have in your system practically to set up the end-to-end secure session? And what is the rate of keys that you can generate?
Okay, very, very good question. Indeed, currently we are experiencing a very, very low key generation rate. Nonetheless, whenever let me say an A to B link is generated, we start collecting encryption keys that can be stored and delivered to the application. In this way, with a buffer strategy, we improve the need of keys from the applications. And there's another part that has to be considered, not only the frequency of generation of the keys, but also the level of security required by the applications. This means how long an encryption key is used during a communication, because I can use the key for a certain time and then renew it. And so the question is difficult to say if the problem is to generate very fast keys or to use them in a very optimized way.
It's a trade-off then, right?
Yeah.
And how long do you need to set up the end-to-end secured session? How long does it take?
How long in which sense? How long does it
that both sides have a valid key and can start to communicate with that key?
Let me say it is a matter of tens of seconds for start having the first part of the key.
Okay, thank you very much.
Welcome.
Okay, thank you for this presentation, and maybe we have time for a quick question. No other questions. Okay, so thank you, and we can move to the next speaker, who is Zhuang Ma from Beijing University of Post and Telecommunications. And I will show the video that was prepared by the speaker, and then the speaker will be glad to answer a few questions from the audience.
Hello everyone, I'm Zhuang Ma from Beijing University of Post and Telecommunications in China. Today, the topic of I'm sharing is demonstration of highly dynamic satellite optical networks supporting rapid reconfiguration. This paper is divided into 5 parts. The first part is background and problem. The second part is architecture of multi-layer satellite networks, and then I will introduce the reconfiguration strategy in satellite optical networks. Experimental demonstration and results will be given in the fourth part. Finally, I will conclude this paper. As we all know, as an important way of communication, the satellite communication network has the advantage of wide coverage, and thus it has attracted worldwide attention. For example, Space Track Company of the United States put forward Starlink project, plan to launch more than 42,000 satellites. The United Kingdom has also put forward the OneWeb project, which plans to launch 2,600 satellites. China has also put forward a series of plans which are expected to launch more than 1,915 satellites. By 2029, the total number of satellites in orbit will reach 57,000. With the dramatic increase in the traffic carried by satellite networks, satellite laser communications with large capacity and high transmission rates are bound to become the future of satellite communications. At the same time, satellite optical networks are facing many challenges, such as large space-time scale, wide area coverage, and high dynamics. A series of key problems need to be addressed, including the rapid reconfiguration, routing convergence, united management and control, risk perception, and value recovery. To verify the feasibility and the performance of the solutions for these key technologies, realistic demonstration platform is required. For the above problems, we first designed the architecture of multi-layer satellite optical networks. As shown in figure on the left, we design a multi-layer satellite optical networks architecture based on SDN. The table on the right shows the specific parameters of each satellite orbit. We choose the GEO satellites to deploy the management and control plan, and each GEO is a sub-controller based on us to control the satellite networks within its coverage. The sub-controller on GEO satellites obtains the link status and resource information of 4 MEU and 25 LEU satellites, and forward the routing information in the domain to the ground main controller for processing. Intra-domain communications is handled by a single sub-controller, and inter-domain communication is handled by multiple controllers. Thus, the GEO controllers are the center of routing decision-making. MEU satellites also serve as the core node of satellite optical networks, which can aggregate and exchange the traffic in the data plane MU and GU satellites from the space-based backbone network together. As original LEO satellites receive data packets from the ground and then send them to the space-based backbone network. Then we proposed a reconfiguration strategy based on adjacent links in high dynamic satellite optical networks. The strategy first build adjacent node set N and link set L of the faulty link, then judge whether alternative path P can be found in set L. You find the path P and in the program and return. You will not find the path P, add a adjacent node to set N and update set L. Then return back to step 2 until find path P and then end the program. Compared with rerouting, this strategy doesn't need to recollect all inter-satellite link status information after a failure of the link. Therefore, the path P obtained by this strategy may not the optimal path, but the calculation is reduced by more than 15% on average, and can quickly recover the impacted service from network failures. The pseudo node code of this strategy based on adjacent links is on the right. So next, we build an SDN-based satellite optical networks demonstration platform and get some delay results of network reconfiguration. As shown in Figure A, the demonstration platform is composed of two parts. One part is a pure software simulation system which contains 200 stock-based satellite nodes. The sound-bound communication with the controller is realized through the netconf protocol. The query and configuration are carried out through the CHIML files. The satellite nodes model of each orbit is built through YARN model, including the laser type, laser port, optical power of the satellite nodes, and so on. The structure of Docker-based satellite nodes is shown in Figure B. The other part is a semi-physical system that's built with software and hardware, including 4 WSS-based transport nodes and management module for communicating with the owner's controller through OVS agent and netconf protocol. As shown in Figure C, this platform demonstrates the communications process of sending video from satellite A to D with 1 Mbps bandwidth. As shown in Figure A, the blue path is the service path of the source node named LEO4 and the destination node named LEO59 before reconfiguration, as shown in Figure B. When the link MU8 to GO3 is at risk, the green path is the rerouting path. It can be said that the configuration caused by link failure only takes 1.41 seconds. As shown in Figure C, for WSS-based optical switching nodes form a ring network in which each node is composed of 2 WSS modules to support the uplink and downlink communication, as shown in Fig D. For the semi-physical system, the reconfiguration delay of node A to D is 4.48 seconds. The delay includes control command generation, onboard processing, and inter-satellite transmission time. The last part is the summary of this paper. First, in this paper, we build an honors-based demonstration platform of 200 stock-based satellite nodes that supports rapid reconfiguration, and the delay is within 3 seconds. Then, we build a ring network of 4 WSS-based optical satellite nodes, and the delay is within 5 seconds. This works verified the performance of reconfiguration strategy in satellite optical network. That's all. Thank you for your attention, and all your comments are always appreciated.
Thank you for your presentation, and we have time for a few questions. So from the audience, please just open your mic and show up with your question, or you can use the chat.
I have a question, Giacomo.
Yes, please.
Just out of curiosity, the last link, which is connecting the LEO satellites to the ground station, which technology do you use? I imagine it is not the optical link. Thanks.
Okay, thank you for your question. We mainly propose a strategy based on sub-adjacent links and adjacent links. It can find the replace path in a small scale links, so it can reduce the loading time of rerouting information.
But is it a radio link between the lower satellite and the ground station?
I'm sorry, pardon. I can't understand clearly your means.
I'm referring to the connection between the satellites on the lower orbit and the ground stations. What do you use to connect these?
We have to simulation the optical links.
Optical, right. Also in the through the atmosphere, optical links.
We use the honors and the Docker virtual Docker nodes, and we defined some ports and laser type in YAM model, and XML files to define some definition the optical links.
Okay,
Okay, thank you.
thanks.
Any other questions?
Maybe one question about the satellite Young model. What is it based on? Is it based on real satellite communication links, or what does it entail? Is it? Can you say something more about it?
The real nodes we best the fiber and it's very long, and we add some etc. time including the time processing on the satellite about 115 seconds for more time, and we use the optical module in 1550，然后we simulation the real links through
Okay, so basically additive delay and data rates that you assume.
Yeah.
Okay, all right, thank you.
Thank you.
Okay, thank you. Any other questions for this speaker? No other questions. So thank you very much for your speech. And we have now the following speech is by Sebastian Troia, and is resiliency in SD-WAN with eBPF monitoring, municipal network and video streaming use case.
Good morning, I'm Sebastian Troia, and today with Marco Mazzara we will present you our demo paper entitled Resilience in SD-WAN with eBPF monitoring, municipal network and video streaming use cases. Let's start by introducing SD-WAN. Business companies use wide area networks to provide services and connect with their branches. Traditional WAN is based on multi-protocol label switching or MPLS. One of the main features of MPLS is that it can provide high connection reliability and speed, but at a high cost of bandwidth and expensive custom edge devices. So to cope with these limitations, from few years now, there is a new technology that is called software-defined wide area network. SD-WAN is a virtual WAN architecture that allows leveraging a combination of different transport services, so not only just MPLS, but also LTE and internet broadband, to securely connect edge network nodes. SD-WAN exploits the software-defined networking advantages in wide area networks, but the main difference is that if SD-WAN has the control over all network elements, if SDN, has the control over all network elements, SD-WAN moves the control over the edge nodes. Business companies need an always-on network to run their services. This means that the SD-WANs must handle a lot of traffic and be resilient enough to withstand disruption failures of networks. To handle these, organizations will need to implement a strong plan for end-to-end resiliency into the SD-WAN in order to ensure efficiency and business continuity. Let's make an example. Let's say that we have a business company with two branches, a headquarters and a branch office, And we have two CPE, one installed at the headquarters and the other one at the branch office. These two CPE are connected between each other through two different networks provided by two different ISP, and the CPE are controlled by an SD-WAN controller that is placed in the cloud. Now, let's imagine to have a service that is running on the first tunnel, and let's say that this service has a delay constraint, that is, if the delay overrun 1.1 milliseconds, this means that we have a failure on this service. So what we want is that our SD-WAN, once we have the failure, so the threshold of the service is exceeding the threshold, we want a fast reaction, so we want that this traffic is moved on the second tunnel that represents the backup tunnel. To do this, we need an efficient monitoring system and a fast traffic routing system. So the objective and our goal is to improve the resiliency in SD-WAN using a monitoring system based on eBPF. What is eBPF? It is a technology that can run programs into the Linux kernel without changing kernel source code. It can be used to monitor different parameters of a Linux-based system, such as the TCP retransmission of traffic flows. The communication between kernel and user space happens with the use of buffers. In this way, a program running in the user space can be used to analyze the information retrieved from the kernel space. So our work can be divided in two parts. So the first part is to develop the eBPF-based monitoring system that monitors the status of TCP connections of servers that are located at the edge nodes, while the second part is the development of an SD-WAN traffic engineering application to configure the virtual CPE according to a specific quality of service threshold. In the previous example, it was the delay. Generally speaking, our implementation comprises two virtual CPE, one at the headquarters and the other one at the branch office, connected by two tunnels. These two CPE are controlled by an ONOS controller, and over the ONOS controller we have the SD-WAN traffic engineering application that is in charge of switching the traffic between the two tunnels. On the left side, we have the server that runs business services. On the right side, we have a local network of the business company. Inside the server, we have our monitoring system. We have implemented our monitoring system that is made by two modules: the kernel agent that is in charge of collecting TCP flows information, and the user agent that is in charge of reading into the buffer this information and trigger the SD-WAN traffic engineering application in case the traffic needs to be switched to the other tunnel. Our virtual CPE are made with Raspberry Pis that are tiny computers that are quite nice to be used in this kind of testbeds. The demonstration can be divided in 5 steps. So the first step is performed by the kernel agent that writes to the buffer the TCP flows information, such as the number of retransmissions. Then the user agent reads the buffer and counts the number of TCP retransmission occurred in a given time interval. Then, if the quality of service threshold is exceeded by one or more TCP flows, then this user agent sends an alert packet to the virtual CPE. After that, the virtual CPE sends this alert packet to the ONOS controller, triggering a packeting event. Then the SD-WAN application reads the payload with the alert packet and triggers the switch to the tunnel 2 for those TCP flows that are running on tunnel 1. We have implemented our SD-WAN solution on 2 different testbeds. The first testbed is called Municipal Testbed. That is a collaboration between Politecnico di Milano and Swan Networks, a spin-off of Politecnico, and the municipality of Militello Val di Catania, that is an Italian town located in Sicily. As you can see from the figure, the testbed is made basically by 2 CPE, one located at the city hall and the other one located at the remote office. They are connected among each other through two networks. The first network is owned by the municipality, is a private wireless LAN, and hence free of charge, while the second network is provided by an internet service provider. So the goal is to run administrative services from this server, mainly on the tunnel 2, that is the private WLAN. And if there is some failure here, to switch automatically the traffic on the tunnel 1. Then we have a second testbed that is called the emulated testbed that represents just a replica of the municipal testbed, but in our lab. We will use these two testbeds to run the two different use cases. The first use case will use the municipal testbed that is called the municipal services use case. The aim is to ensure that administrative services between the city hall and the branch office are restored as soon as a network failure occurs. So we have run 10 TCP flows from the server to the remote office, and we add packet loss on the primary path, and plot the retransmission on live graph. We will see how our SD-WAN solution will react. Then we have performed another specific experiment, the video streaming use case in the emulated testbed. Here, the aim is to demonstrate the effects on delay-sensitive services when reconfiguration occurs to adapt to changes on network state. A host connects to a video streaming on the remote server, and then, even in this case, to test our solution, we add packet loss on the primary path to see how our SD-WAN solution reacts. Now, Marco will show these two experiments with two videos.
In this video, we show the screen recording of the server. On the right of the screen, we can see the terminal of an Open vSwitch Raspberry connected to the primary and the backup tunnels, and two terminals of the server. On the left, we start a Python script that uses matplotlib to show live the retransmissions detected by the monitoring system. We start 10 TCP flows from the server to a remote host using DITG, and we start the monitoring system without the alerting feature, just to trace retransmissions. The generation of packet loss on the Raspberry, first 1% and later 10%, shows how the retransmissions are detected by the monitoring system of the server. The packet loss is stopped, and we can see on the graph the dots representing the maximum number of retransmissions per second for each connection. This time, we activate the monitoring system with the alerting feature using a threshold of 40 retransmissions per second. As long as the packet loss stays below the threshold, the connections do not alert the monitoring system. On the other hand, as soon as the threshold is exceeded, the path switch mechanism is activated and the retransmissions are zeroed. In this video, we show the screen recording of an host having, at the bottom of the screen, two terminal sessions, the remote video server on the left and an Open vSwitch Raspberry connected to the two tunnels on the right. The top right window shows the OpenFlow rules installed by our ONOS application on the Raspberry. First off, we open VLC to connect to a video streaming running on the remote server. The cache is reduced to make the streaming more sensitive to packet loss. On the right, we can see the rules that are installed to route the traffic on our primary tunnel with priority 100. The video starts playing. We now generate packet loss on the Raspberry on the primary link and wait to see the effects on the video. The packet loss is removed, and now we will try again activating our monitoring system on the server. As soon as we issue the packet loss, the monitoring system detects the retransmissions, and we can see that the ONOS app installs rules with a higher priority to route the traffic on the backup tunnel. We see that this time the video has no glitches and continues smoothly. We issue again a packet loss, but this time on the backup link. In this case, once the monitoring system detects the retransmissions, the ONOS app removes the rules with high priority and the traffic is routed back on the primary path without any problem.
This ends our presentation. So I would like to thank the municipality of Militello Val di Catania for hosting our testbed. But more important, I want to thank Mario Troia, that is the head of the IT office at the municipality of Militello Val di Catania. He was my dad, and he passed away a few weeks ago. So I really want to thank him for his support, and since thanks to him, we were able to run not just these kind of experiments, but many others. So thank you. Now it's time for questions.
Hi, John.
I thank you for your presentation, and there is already one question in the chat from Francesco Paolucci. Very nice demo. Do you think eBPF solution may be used to monitor additional QoS metrics such as latency, e.g. using two monitors co-located at the tunnel edges?
Well, in principle, I think yes. Since you have access to the kernel, you can monitor also other metrics that can be on the other layers of the stacking protocol, right? So basically, yes, you can do that, I think.
So any other questions? I have a quick question regarding your usage of eBPF. There is now a lot of hype about eBPF, and a number of companies are releasing smart NICs that can execute eBPF. Is your solution capable of taking advantage of smart NICs using eBPF, or this is something that is not suitable?
I think yes, because the code that we wrote for this testbed is potentially open to be applied also to smart NICs where eBPF is implemented, and clearly we don't have this smart NIC. We have run this on a server, where there was a Linux kernel. But this is the powerful of BPF, right? Where you can write codes even emulating on a simple operative system, and then you can adapt your code also to the smart thing. And there, of course, you can exploit many more metrics to adapt to traffic changes. Definitely is something that we will do.
Any other questions for the speaker? Just open your mic and put your question. Mr. Troia is eager to answer all your doubts. I have another quick questions. So you are monitoring TCP retransmissions in order to assess the quality of the communication, but TCP retransmission might originate from problems in various links of the network. Aren't you running the risk of attributing the problems to the link that you are monitoring, whereas the problem might be somewhere else?
Well, this is the somehow something that, of course, you're right. Every time you change the path of your traffic, you are taking a risk because it could be related to something else, right? But this is actually one of the challenges of SD-WAN, which you can have a problem in the network, but you don't have power, you don't have control of that network. So somehow you have this trade-off. You have to monitor not just one TCP flows. You have to monitor all TCP flows, and if there is a problem on just one or two, maybe it's not related to the network. Maybe it's related to other to some problem that is at the edge, directly to the client, for instance, right? But if the number of retransmission of is increasing for many TCP flows, maybe then there you can assume that there is a problem on a link on that network, and then you take the risk to change. But this is an open challenge in this case.
Okay, thank you. And
thank you.
We can move to the final speech of today's demo session. User plane function offloading in P4 switches for enhanced 5G mobile edge computing. And the speaker is Francesco Paolucci. I'm going to share the presentation.
Good morning, everybody. My name is Francesco Paolucci, and I'm going to present this paper accepted to DRCN demo papers zone. I want first to thank the co-authors of this work, which are Davide Scano, Andreas Gambelluri, Luca Valcarenghi, Piero Castoldi from Scuola Superiore Sant'Anna, Filippo Cugini from CNIT, and Carlo Cavazzoni, Giuseppe Ferraris from Telecom Italia. Title of this paper is a user plane function offloading in P4 switches for enhanced 5G mobile edge computing. So as an introduction to this demo paper, we are going to consider selected 5G functions in the multi-access edge computing platform that can be offloaded to programmable hardware. Typically, they are deployed as a virtual network function. But in this case, the SDN network programmability, which is raising in the last years, may play a key role for example, resorting to agnostic P4 language to program the network hardware. So the idea is to resort to these data plane programmability capabilities that are going to be increased in the last years, and to get benefits from existing network devices. The current research trends that are considered so far is the application of FPGA for selected functions such as GPRS tunneling protocol, stateless translation in segment routing, and 5G virtual RAM functions to programmable hardware. In this demo, we will show the implementation of a 5G user plane function offloaded in a P4 switch, programmable switch. The implementation is carried out on the behavioral mode version 2 switch, which is the reference software switch provided by the p4.org organization. That includes GTP operation, encapsulation and decapsulation, steering, and postcard telemetry. And this will show the demo comprehensive of a network testbed showing latency, scalability, and online monitoring. So let's first discuss what is the 5G user plane function. The main role of the UPF is to map incoming and outgoing traffic from each distributed G node B and the edge and cloud gateways. They are typically implemented in a virtual environment in the IT space, so they can be implemented either in the edge or in the cloud. And the role is basically to map IP flows to GPRS tunneling protocol user tunnels to reach the closest G node B, and then apply the 5G stack in the radio access part. In the case of 5G UPF, multiple gateways are allowed. So multiple GTP tunneling are allowed. You can see here 2 UPF connecting, for example, a edge data center with a central cloud data center. And the standards so far have considered different interfaces. The interface N6 that connects the UPF towards the local data net gateway, this one. The interface M3 towards the closest G node B, where there is a GTP encapsulation, and interface N9 towards an additional UPF device, resorting to another encapsulation type, which is the same type of GTP, but with another tunnel ID. So all these functions need to be considered in the development of a user plane function device, and or also virtual machine. So what are the operations that we are going to consider in the P4 switch? First, the encapsulation of IP traffic to GTP tunnels. So first, the switch is implemented to consider and process all the parsers related to each received packet. So in this case, we consider Ethernet, IP, UDP, and GTP protocols. In the case of GTP header is not present in the stack, the switch is programmed to perform the execution of a table named the table encap GTP. You can see here the structure of the table implemented in P4. Based on flow entry matches, this table selects the actions to create the encapsulation action. So basically, the encap GTP action is executed by matching the IPv4 destination, source, and protocols to perform the GTP encapsulation. Here you can see the action of the creation of a new IP, UDP, and GTP stack by considering the insertion of a new IP header, a new UDP header, and a stack of GTP protocol you can see here. So the idea is to create this green header stack on the existing blue stack. And this is simply performed by adding a flow entry by specifying the match fields and the outgoing parameters of the label stack, in particular the GTP gateways replaced in the IP destination and the tunnel ID value in the GTP header. Besides encapsulation, we perform also decapsulation actions. So in the case the GTP header is present, then a different table is executed in the before pipeline. And this is the table decap GTP. So the match is done on the tunnel ID of the GTP protocol. And based on the flow entry matches, this action is able to set the GTP stack headers as invalid, thus imposing their removal from the packet. So basically, all the green stack will be simply set as invalid and then removed from the parser stage of the P4 switch. And the match is done via flow entry by considering the TAID value for the incoming packet. And this is simply performed by adding a simple flow entry. This is the table, and this is the actions or the decapsulation. We are also considering the full UPF steering options, so that to enable full interfaces operation and forwarding. In particular, forwarding decisions are included in the NCAP and the CAP tables to consider the output port selection via flow entry. So we just added the standard metadata egress specification port by considering the output port, the related output port, so to provide the forwarding. And also to provide the swap operation between interface N3 and interface N9, the table decap GTP is extended to support the GTP tunnel swap. So a novel mutually exclusive action, which I've called the set output change tunnel ID, is responsible to swap the tunnel ID. And you can see here the action that is done. So the match is again made via flow entry. So the TAID value in the GTP header is matched, and then selected the new one to be enforced on the new protocol stack. So in this case, so the full steering is allowed. Physical interface independency is guaranteed, along with the on-the-fly reconfigurability and slicing a virtual interface ready. So the capability to perform all the desired forwarding action on the desired flow, regardless of the physical interfaces. So each physical interfaces can act as a logical UPF-based interface, simply adding the related flow entries. Besides the GTP operation, we have implemented in the P4 switch metadata monitoring. In particular, we are interested to monitor the latency that is experienced at each UPF, which is a key metric for 5G performance. In this case, we have implemented a postcard-based telemetry at the switch that simply analyzes the metadata available at the P4 switch and make them available through a dedicated monitoring interface to be analyzed by external monitoring platforms. The flows to be monitored are selected again via flow entry, and the selected packets are mirrored, transformed in telemetry report packets, and provided to selected monitoring outgoing interface. The report packet includes the hop latency experienced by the packet, and this is a packet metadata that is typically available at the P4 switch, in particular at the BMV2 implementation platform. We have performed switch performances in order to evaluate the 5G scalability, considering the BMV software switch, applying a constant bitrate scenario traffic, And the result is to analyze the behavior of the switch, considering different load, incoming load, and measuring the latency that is experienced by the switch with a configurable number of active flow entries, meaning that we consider different number of flows to be treated as GTP tunnels, from 1 flow up to 10K. Here we can see that we have the switch working range that typically depends on the software switch CPU clock. And so here you see that there is a dependency on the number of the flow entries that we install here, but within the working range of the switch, the latency is quite constant. So within the working range, it is almost content is the range 200 microseconds. So the result is that the UPF function in the P4 switch in the working range of the software switch are scalable with the number of flow entries. So in terms of number of controlled flows and as a function of the size of the network in terms of served users. Another performance is considered by evaluating the impact of the GTP tunneling operation with respect to baseline forwarding. So by comparing the latency experienced by the switch with the simple forwarding and considering the combined forwarding and GTP operation. So what is the impact of the UPF specific functions with respect to standard forwarding? And within the working ranges of the switch, the latency is quite negligible in the sense that the contribution of the GTP operation with respect to standard forwarding is quite negligible. And so this means that the UPF function themselves are offloadable with a limited impact in terms of latency. We have realized the demonstration testbed based on the code, the P4 code that we have shown so far, implemented in 3 BMV2 software switch over bare metal their service, connected using gigabit Ethernet interface ranging from 1 gigabit Ethernet interface up to 40 and 100 gigabit Ethernet. The traffic is generated by the Spirent N4U traffic analyzer. The programmable switch Mellanox SN 2010 switch is acting as a transparent G-Node B. And basically we are going to create 2 flows, flow 1 to flow 2, F1 to F2, it's flow 1, that traverse the N6, N3, and N6 path, so providing encapsulation and decapsulation, and the F1 to F3 flow that performs encapsulation, swapping here at UPF2, so the change of the tide here from N3 to N9, and then final decapsulation. Moreover, there are a dedicated monitoring interface at UPF1 and UPF2 connected to a report interpreter application and an InfluxDB database and Grafana graphic user interface that is able to analyze the online data that are received and processed by UPF1 and UPF2. These are some photos of the testbed. These are the programmable Mellanox switch. These are the P4 switch implemented over Dell servers. And this is the Spirent N4U traffic analyzer and generator. Here I have provided a video of the testbed showing how it works. So I can describe here. We are inside the Spirent N4U, and in this moment, we are programmed all these flows. Basically, they are UDP flows. We are started F1, F3, and F2, F3 so with the rate of 100 packets per second. Here we are at the UPF1, and we see the packets that are received and transmitted. So at UPF1, we first analyze the N6 interface, and you can see that there are two kinds of flows, UDP flows destined to 10.20 and 10.30. It is a standard UDP traffic, and that's a constant bit rate that is flowing. And at this point, we are going to snip the traffic at the N3 interface. And so you can see that the traffic is mapped into GTP tunneling protocol. And the different tunnel ID, which are the first terminates with 8 and the second terminates with 12, related to the different flows. So this is what UPF1 does. If we are going to see what happens at UPF2, you can see, just a moment to load the Wireshark, the receiving interfaces coming from UPF1 receives GTP traffic from both flows, so .30 and .20. If we take a look to the interface connecting UPF2 and UPF3, so the N9 interface, there is only one flow destined to 1030. And you can see that the tunnel ID has changed. So it terminates now with 99, meaning that we have provided the swapping of the tunnel. We can take also a look to the monitoring interface. Here you can see that each packet represents a report packet of a GTP packet and provides data about the UPF switch, in this case 0B switch, and the flow ID that we are considering, along with all the timestamps and op latency and metadata that will be provided to the InfluxDB and Grafana. And here you can see the online Grafana graphic using interface dashboard showing the average latency experienced by the two flows in the two switches, switches 0A UPF1 and switch 0B UPF-B. You can see here that the average latencies are in the order of 30, 40 microseconds. If now we are adding additional traffic, 8,000 frames per second for each flow that is flowing now in the testbed, we can see here that the latency does not change substantially. Yes, there is a peak here, but the average value is not changed so much, meaning that the application of additional traffic within the working range of the switch maintains the experienced latency inside the range 30, 40 microseconds, as demonstrated by the results that we have showed so far. And this is the end of the video. We can jump to the conclusion. So jumping to the conclusion, the demo has shown an implementation of 5G UPF functions offloading inside an SDN programmable P4 switch. The demo showed that the offloading is feasible, is scalable, and with a limited impact on the switch performance. The proposed switch design allows easy online reconfiguration of flows and interface via flow entry, for example, without needing further P4 coding. And the P4 metadata exploited to perform postcard-based telemetry is about latency, providing an online monitoring on flows for online detection of QoS and latency performance of the 5G flows. So thanks for for the attention. I also would like to acknowledge the projects that carried out this activity. First of all, the cooperation agreement between Telecom Italia, Scuola Superiore Sant'Anna for the 5G MISE trial in Bari and Matera, the Brainy project funded by Excel Joint Undertaking and funded by the European Commission, and finally the Department of Excellence in Robotics and AI funded by MIUR Scuola Superiore Sant'Anna. So this concludes my talk, and thank you very much, and welcome for any question. Thank you.
Giacomo, you are muted. You're on mute.
Thank you, Guido. Okay, so thank you to the speaker, and please make your questions. We already have one question on the chat from Sebastian Troia. Congratulations for the very nice work. I have a question about security. Is it possible for an attacker to change the green headers, IP, UDP, and GTP?
Yeah, thanks for the question. Can you hear me?
Yes, loud and clear.
Okay, so we haven't afforded the theme of the topic of security in this work because we were committed to understand the potential of UPF offloading in P4 switches and the performances. However, it's something that could be taken into consideration, because if an attacker has the capability to enter the P4 switch, or simply modifying the P4 code and sending different P4 codes, this of course can affect the performance of the switch. So I would say what we have to take care is the security of the control plane that performs the configuration of the switch. I don't know if I answered. Okay, I see. Okay, thank you, Sebastian. Okay.
Perhaps I have a question stemming from your presentation, and my understanding, and this is what you generally see in the developer forums, is that BMV2 is something designed for development and not for production. But nonetheless, I've seen it crawling into production, and I've seen several researchers assessing performance using BMV2. So how do you think it will be the future of P4 over software runtimes?
That's a very good question. We use BMV2 for the simple reason that this is the reference software switch for P4 and enables all the potential and capabilities of the P4 languages. That said, of course, the BMV2 is not designed for performance, okay? So only to exploit of all the P4 capabilities. And so there are some projects, ongoing projects and open source projects that are trying to provide open source switches programmable with P4 and considering also performances. There are some open source projects based on OVS, and people are working on that. We have a collaboration with a guy from Orange Labs that is developing a switch derived from Open vSwitch with very high performance, able to sustain a overall throughput of up to 40 gigabit per second. However, the current problem of this kind of switch now is that they do not provide the full capabilities of the P4 languages. So they are limited to certain, let's say, parts of the P4 language. That they cannot exploit everything available in the P4 language. That's the gap that we are trying to fill.
Thank you. Other questions from the audience? No other questions from the audience. So thank you for your presentation and very nice demo.
Thank you, Giacomo.
This closes our session, our demo session, which is something new in DRCN. And I think we can be satisfied and with this new demo session. Okay, so Professor Meyer, the floor is yours.
Thank you very much, Giacomo. And thank you all the speakers. I think this demo session is something that is a plus. Now I would like to, before wishing you a good lunch, I would like Gianfranco Elia to switch on his camera, please. Gianfranco, are you there? If you are there. Okay, so Gianfranco will not be attending the closing session, but I would like to thank him for all the technical support that he gave us, constantly monitoring the sessions and also recording the videos and so on. So a virtual applause to Gianfranco from METID Politecnico di Milano. Thanks.
Thank you, Guido. Thank you very much.
Okay, so we have the lunch break now, and following the previous days, I would like to point out the last plat du jour, in order to, since this is the last day of our conference, I would like to finish with the dessert. This is the traditional panettone from Milano. We have then the last event, which is the workshop that will start from starting from 2 o'clock. So please welcome back at 2 o'clock. In this workshop, we will deal with programmable data plane, which in a sense has been introduced very effectively by the last demo presented by Knip. And therefore, let's get back at 2 o'clock. At the end of this workshop, we will have the last keynote speech of the conference by Professor Nick McCune, and then the closing session. Okay, so see you later, and thank you. Thanks.